The universe is an enigmatic expanse, brimming with a myriad of marvels that never cease to captivate and astound us. But among the many awe-inspiring phenomena that occur in the cosmos, few are as dramatic and explosive as stellar collisions. These incredible events involve the collision or merger of two or more stars, unleashing an incredible amount of energy and creating some of the most fascinating objects in the universe. From the formation of new stars to the birth of black holes and the creation of heavy elements, stellar collisions have played a key role in shaping our universe as we know it today. In this video, we'll take a closer look at the different types of stellar collisions and explore the incredible phenomena they create. Binary star mergers occur when two stars orbiting each other come too close together, and their gravitational forces cause them to merge into a single, more massive star. This process is known as a stellar merger, and it can have profound effects on the surrounding environment. There are many different types of binary star systems, but the most common are those where two stars of similar mass orbit each other. As they orbit, the stars can exchange mass and energy, which can cause their orbits to change over time. If the stars get too close to each other, their gravitational forces can become so strong that they begin to merge. During a binary star merger, the two stars spiral towards each other, releasing vast amounts of energy in the process. This energy is mostly in the form of gravitational waves, which are ripples in space-time that travel at the speed of light. As the stars get closer together, they begin to heat up and emit intense radiation, including X-rays and gamma rays. The merger process itself can take anywhere from a few hours to several days, depending on the size and mass of the stars involved. When the stars finally merge, they create a single, more massive star that is often surrounded by a disk of gas and dust. This disk can be incredibly bright and can emit large amounts of radiation, including visible light. Binary star mergers can produce some of the most exotic objects in the universe. For example, Neutron star merger can produce intense bursts of gamma rays, which are some of the most energetic events known to humanity. Another type of binary star merger involves a white dwarf star and a companion star, which can also be a white dwarf. When these two stars merge, they create a type of explosion known as a type 1a supernova. These supernovae are incredibly important because they are used as standard candles to measure distances to far galaxies. Few events can match the sheer spectacle and scientific significance of type 1a supernovae. These cataclysmic explosions occur in binary star systems when a white dwarf, a dense stellar remnant, reaches a critical mass threshold, triggering a chain reaction that culminates in an extraordinary release of energy. To comprehend the nature of type 1a supernovae, we must first understand their formation process. These incredible celestial fireworks owe their existence to the intricate dynamics of binary star systems hosting a white dwarf and a companion star. The companion star can be a main sequence star or another white dwarf. As the binary system evolves over millions of years, matter from the companion star accumulates on the surface of the white dwarf, gradually increasing its mass. As the white dwarf's mass nears a specific threshold, known as the Chandrasekhar limit, which is approximately 1.4 times the mass of the Sun, a dramatic chain of events is set in motion. At this critical point, the immense gravitational pressure squeezes the white dwarf's core, causing it to become incredibly hot and dense. Within this compressed environment, carbon and oxygen nuclei begin to undergo nuclear fusion, rapidly releasing a tremendous amount of energy. The ignition of nuclear fusion reactions within the white dwarf's core unleashes an explosive release of energy that tears the star apart. The resulting explosion ejects vast amounts of matter into space at velocities exceeding thousands of kilometers per second. One of the most remarkable aspects of type 1a supernovae is their incredible brightness. These cosmic beacons can outshine entire galaxies for several weeks, often reaching peak luminosities millions of times greater than that of our Sun. The brightness, however, follows a distinctive pattern known as the light curve. Initially, the supernova brightens rapidly, reaching its peak luminosity within weeks, and then gradually fades over the span of months to years. Type 1a supernovae serves as standard candles, objects with known luminosities, allowing astronomers to measure vast cosmic distances. By comparing the observed brightness of distant Type 1a supernovae to their expected luminosity, scientists can determine the expansion rate of the universe. This groundbreaking discovery led to the realization that the universe's expansion is accelerating, indicating the presence of dark energy, an enigmatic force driving this cosmic expansion. The explosive nature of Type 1a supernovae gives rise to another extraordinary aspect: the production of heavy elements. Within the intense heat and pressure of the explosion, atomic nuclei collide and fuse, creating elements such as iron, nickel, and other elements beyond the range of ordinary stellar fusion processes. These ejected materials enrich the interstellar medium, providing the building blocks for future generations of stars and planetary systems. The merging of neutron stars is a cosmic phenomenon that never fails to captivate and mesmerize with its rare and enchanting spectacle. These collisions occur when two neutron stars, the incredibly dense remnants of massive stars that have exploded in supernovae, come together in a violent collision. The resulting explosion sends ripples through the fabric of space-time, creating gravitational waves that can be detected by sensitive instruments on Earth. The process of neutron star mergers is incredibly complex and involves a number of different physical phenomena. As the two stars approach each other, they begin to spiral inward due to the force of gravity. As they get closer and closer, they begin to distort each other's shapes, creating intense gravitational forces that cause the stars to emit enormous amounts of energy in the form of X-rays and gamma rays. Eventually, the two stars collide, creating a massive explosion that sends shockwaves through the surrounding space. This explosion is so powerful that it can create heavy elements like gold and platinum. One of the most exciting aspects of neutron star mergers is the fact that they produce gravitational waves. These waves were first predicted by Albert Einstein's theory of general relativity, but it wasn't until 2015 that they were actually detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Since then, scientists have detected several more gravitational wave events, including a neutron star merger that occurred in August of 2017. This event was particularly exciting because it was the first time that both gravitational waves and electromagnetic radiation were detected from the same source. By studying the properties of these waves, scientists can learn more about the nature of gravity, the structure of space-time, and the behavior of matter under extreme conditions. The next objects we'll explore stand as a testament to the universe's boundless capacity for wonder and intrigue. These rare and elusive objects were first proposed in 1977 by astrophysicists Kip Thorne and Anna Zytkow, but it was only in 2014 that the first candidate was discovered. These objects are formed when a neutron star collides with a red giant, resulting in a hybrid object that is unlike anything else in the universe. One of the most interesting aspects of these objects is their unique composition. When a neutron star collides with a red giant, the resulting object is a hybrid of the two. The core of the red giant, which is primarily composed of helium, merges with a neutron star's outer layers, which are made up of heavy elements like iron and nickel. Thorne-Zytkow objects are thought to have a dense core of neutrons surrounded by a shell of lighter elements. The outer layers of the object are thought to be composed of hydrogen and helium, with heavier elements like carbon and nitrogen mixed in. Thorne-Zytkow objects are also thought to be incredibly luminous, emitting large amounts of energy in the form of light and heat. This is due to the fact that they are still undergoing fusion reactions in their outer layers, even though their core has collapsed into a neutron star. In 2014, astronomers announced that they had discovered a possible Thorne-Zytkow object in the Small Magellanic Cloud. This object, known as HV 2112, was found to be emitting unusual spectral lines that could not be explained by any known stellar type. However, later in 2018, this object was excluded from the list of candidates, but a new candidate was proposed instead, HV 11417. From the fiery cataclysms of supernovae to the enigmatic Thorne-Zytkow objects, each collision holds its own unique story and reveals a new facet of the cosmos. As we continue to explore and unravel the secrets of these celestial collisions, we are humbled by the sheer magnitude and complexity of the universe and reminded of our place in this awe-inspiring cosmic dance.